One of the topics, and it's quite a different topic, but it shares a lot of the common interest in the life cycle properties that we're working on with NASA, is designing future space exploration systems for potentially going back to the moon, going back to Mars, or even visiting asteroids. And so there is some uncertainty right now in the US space program as to what the next destinations will be or should be, but we can't stop exploring. So we have to continue developing both launch systems, crew support systems, and also robotic explorers that will allow us to really take the next steps in space exploration. And so the methods that I talked about for ground-based systems like desalination systems at an abstract level also apply to systems in space. And so we, for example, are currently working on a program called HabNet that will allow the design of flexible habitation systems that can support a small crew initially, including the water management, the air revitalization system, and then expansion, if successful, eventually expand in a modular fashion. The traditional view of space exploration is we do one mission at a time. We explore here, we come back, we explore there, we come back. We believe that the future will be to build up gradually an infrastructure in space. So one mission builds on the next, and typically we talk about campaign planning. So we are thinking about how do you really do campaign planning where you develop really a resource economy in space. So for example, first you develop an exploration vehicle for a short-term visit. Maybe you leave behind what's called an in-situ resource utilization plant. You can produce oxygen on the moon. We know this, the technologies exist, but it isn't clear the best way how to deploy it. Where would you store these resources? There's a lot of interest in asteroids and near-Earth objects. What could their role be in future expansion of future activities in space that eventually we're hoping will become self-sustaining? One of the things that is really exciting about space exploration and making humans survive and thrive in space is that you have to be extremely efficient. Everything you bring with you has to be used and reused over and over again. So the current loop closure rates, for example, for water on the International Space Station is about 80%. And so our models predict that if we want to go to Mars and really stay there for a long term, we will need to achieve at least 95–96% loop closure. And so that is something we cannot yet achieve. And so this work that we're doing, the research that we're doing in modeling and simulating closed loop systems helps us set targets for technologies we need to develop to achieve that goal of long-term human presence in space. And of course, by pushing the envelope on that, we are hoping that there will be benefits on Earth, that some of these technologies will be adapted and will help us become more efficient on this planet. Because in a sense, the Earth is itself a spaceship. We are all here together on a big spaceship, and we're starting to see the limitations of resources, what we do with our waste. And so I do see a strong crossover between thinking about closed-loop systems in space, evolving ourselves as a multi-planet species, and becoming more efficient, more thoughtful in how we use resources on this planet.